Hi everyone. Now I am going to discuss metal excess defect due to presence of extra cations at interstitial sites. For this, best example is zinc oxide. Zinc oxide crystal lattice at room temperature at RT. RT means room temperature. At room temperature, its color is white. The color of zinc oxide is white. Whenever it is heated, then it loses, this zinc oxide crystal lattice loses 2 electrons and it becomes zinc plus 2 and oxygen gas is liberated. See here how the presence of extra cations at industrial sites I'll discuss here. So by giving this rough figure, for example, this is zinc plus 2 ion, this is oxygen, this again zinc plus 2 and this is oxygen. Similarly, this is again here I'm writing directly zinc, this is oxygen, zinc and oxygen. Here oxygen, it should be zinc. This is oxygen, again zinc. Similarly, this is zinc and oxygen. Here zinc and this is oxygen. Now whenever this zinc oxide lattice, crystal lattice solid is heated, then oxygen, one of the oxygens here again liberated as or escape out from this lattice as O2 gas. So here one of the oxygen, this oxygen I am taking, this oxygen is missing from here, missing from this lattice and liberated as oxygen gas, and it releases 2 electrons. That means zinc plus 2, one of the zinc here from any of this zinc, any of sphere which is related to zinc, now enter into interstitial site as zinc plus 2 ion, because to maintain electrical neutrality, number of positive charges must be number of negative charges. Almost all crystal lattices, even after defect also, they maintain electrical neutrality. So here also to maintain electrical neutrality, see after liberation of this oxygen gas from the zinc oxide solid after heating, the electrons released enter into adjacent or alternate interstitial sites, not like metal excess defect due to anion vacancies. In anion vacancies, electrons enter into directly the site in which negative ions are present before. Here it is not like that. Here this is directly anion vacancy, like that only, anion vacancy. And equal one more here beside this or here or from here, this I am taking. So this zinc is eliminated. This is cation vacancy. This is cation vacancy. Both are present here. Anion vacancy is present. Cation vacancy is also present. But this cation not escaped as a gas like oxygen, like anion. See here this zinc now change to zinc plus 2 and enter into one of the industrial site. Here we can take this zinc, means here it enter into this industrial site. Here I am writing as zinc plus 2, as zinc plus 2, and remaining the electrons are present here. Those electrons now occupy adjacent to adjacent interstitial site to this zinc plus 2, means here and here. Here I am writing clearly, this is the interstitial site now. So what bigger I am writing, this is the interstitial site. From here O minus 2 is eliminated as oxygen gas, and here now zinc will enter. Zinc will take this position. This is anion. This is not anion vacancy. This is anion vacancy. This is industrial site. This industrial site occupied by zinc, means here one of this zinc site which is within the lattice now vacated, and that zinc is enter into interstitial site. So here see metal excess defect due to presence of extra cations at interstitial site. extra cations means this zinc which is present before this before at this site now leaves its site. It is dislocated from this side. It is dislocated from this side and enter into the interstitial site as zinc plus 2. The two electrons are present here. Here one electron, here one electron. So due to these electrons, due to presence of these electrons in interstitial sites, whenever this zinc oxide is heated, these electrons now absorb energy from the light and they get excited. Due to this excitation, it can import which color? Again yellow color. Why zinc oxide becomes yellow? Generally, here due to excitation of electrons only, we have colors. Due to excitation of electrons. Those electrons are due to what? That you have to remember. Those electrons are due to this reaction. See, zinc oxide when heated, zinc plus 2, oxygen gas and 2 electrons. These 2 electrons are entrapped here in the interstitial sites. And zinc plus 2 also dislocated from its original site and entrapped into interstitial site. So these electrons are now occupy the adjacent interstitial site to that of zinc plus 2 ion. So that it maintains electrical neutrality. Now if you count here, number of zincs are more compared to number of oxygens. So number of metals are more compared to oxygens. So that we can say it is metal excess defect. Okay. Similarly, we have metal deficiency defect also. It is also important. So this is about metal excess defect due to extra cations are present in interstitial site. Best example is zinc oxide. Its color is yellow after heating. Before heating at room temperature, its color is white. The color is due to presence of these electrons, but not this is F center. Remember, these electrons are present at interstitial sites. Interstitial sites are not considered as F centers. F center is nothing but it is anionic vacancies only. And this metal excess defect due to presence of extra cations are related to zinc oxide like examples which can show Frenkel defect also. In Frenkel defects also we have discussed like these examples. So Frenkel defect related examples we can consider here. Then next defect is metal deficiency defect. In non-stoichiometric defects we have two types I told earlier. One is metal excess defect, other one is metal deficiency defect. In metal excess defect, we have two types. One is anionic vacancies, other one is presence of extra cation in or at industrial site. Now, metal deficiency defect. Metal deficiency defect. In metal deficiency defect, here first I write this the metal deficiency is less deficiency defect. For this, we should know some conditions. What are the conditions? First thing is metal deficiency defect. For this, first of all, that metal which is present in the crystal lattice must show variable valencies. So, metal must show variable valency, means more than one variable valency, more than one valency or oxidation number. Generally, more than one valency means it is related to transition elements. Transition metal compounds or transition metals in their compounds or in different compounds they show variable valencies so that these are applicable for transition metals and their compounds or metal compounds I am writing here. Transition metal compounds generally show metal deficiency defect. So these are the two conditions obeyed by that particular crystal lattice. First one is metal must show variable valency. That variable valency is for transition metals. So transition metal compounds we can expect. See here I am taking this example. Iron oxide, ferrous oxide we can take. Then ferrous sulfide we can take. or nickel oxide we can take, nickel sulfide also we can take. So the general examples for metal deficiency defect. Metal deficiency defect. Here metal deficiency defect, in this stoichiometry of the compound is disturbed. Again, it is considered non-stoichiometric defect due to missing of either cation or anion or both disturbs the stoichiometry of the compound. So, if you take here iron, whenever it is heated up due to this defect, it may changes from 0.93 O. Otherwise, 0.96 O. That means the range of this irons here are 0.93 to 0.96. Otherwise, we can write it as FeXO. What is X value? X value what I written here? Here X is equal to 0.93. The range is 0.93 to 0.96. Similarly, iron sulfide or nickel oxide, nickel sulfide also we can write in the same way. So metal deficiency defect is related to transient metal oxides or transient metal sulfide. Transient metal compounds means maybe here oxides and sulfides. Oxides and sulfides. See here why we should consider transient metals and variable valency is important here. Why we can consider variable valency? What is the use? Means again to maintain here also to maintain electrical neutrality. In other defects, in metal excess defects, electrical neutrality is due to compensation of the positive charge by electrons. Stoichiometry is disturbed, so that they become non-stoichiometric defects. But some of the anions are missing from their original sites, due to which metal becomes indirectly excess there. So that we can say metal excess defect. But the electrons which are occupy the interstitial sites in extra cations at interstitial site. Otherwise, the electrons which are present at F centers can maintain electrical neutrality, and that is the cause, that is the reason for color also. Right. But here, to maintain electrical neutrality, electrons concept is not present here. Here, directly only metals are missing from the original side. Metals are plus 2. Here in all these, Fe plus 2, here Fe plus 2, nickel plus 2, nickel plus 2 state is present. So that plus 2 ions are missing from their original sites. Whenever metal ions are eliminated or missing from that original site, how they can maintain electrical neutrality? If they do not maintain electrical neutrality, then that substance becomes unstable. Always neutral substances are stable, and any charged species you can take, they are unstable. So here also to maintain, if they maintain electrical neutrality, then only they can get stability after even defect also. If they are not maintaining electrical neutrality, means they will not get stability. So here also they will maintain electrical neutrality, but how? So to maintain electrical neutrality, some of plus 2 ions are changed to plus 3 ions. So here to maintain electrical neutrality from iron oxide, if you take this as example, so here see 3 Fe plus 2 ions are changed to 2 Fe plus 3 ions. See here, how many irons are missing from here? 3 irons are present here. Just observe. Here only 2 irons are present. Without charge, just assume. Here 3 irons are present. Here 2 irons are present. One iron is missing from here. So metal is one metal is missed. There is no change in oxygens. Number of oxygens are same, or number of sulfurs are same. But one metal is missed from here as +2. Generally, lower oxidation number, lower valency metal can miss it from the lattice. So, higher valency metals may maintain electrical neutrality. Means some of lower valency metals, metal ions are changed to higher valency metal ions to maintain electrical neutrality. See here, one iron is missing from here. One iron is missing from here. But 3 into 2, 6 positive charges are present. Here 2 into 3, 6 positive charges are present. So that it maintains, there is no change in charges once you observe. Here also 6 plus 6, here also plus 6. No change. But metal is missed. So after missing of even metal ions, there is no change in charge. Why it is so means Fe 3 Fe plus 3 plus 2 are converted into 2 Fe plus 3. That means one Fe plus 2 is eliminated, and from the same side 2 Fe plus 2 are converted into Fe plus 3. So here I give some rough explanation for understanding, only understanding purpose I am giving here. See here, for example, in FeO 100 Fe plus 2 ions are present. And here FeO, if you take 100 Fe plus 2 ions, there should be 100 O minus 2 ions. There should be 100 O minus 2 ions. So how many positive charges are present? 200 positive charges are present, and similarly 200 negative charges are present. 200 positive charges get cancelled by 200 negative charges, so it becomes neutral. So it is neutral means it is stable. But due to this defect, for example, from this 100, 1 Fe plus 2 ion is missed. 1 Fe plus 2. This is original. Now from this, one of Fe plus 2 ion is missed means now 99 Fe plus 2 ions are present. If 1 Fe plus 2 is missing, so now it becomes 99, and oxygens remain same, 100 O minus 2. So how many here? 1 plus 2, no? 99 into 2, 198 positive charges are present, and 200 negative charges are present. But so it will not give electrical neutrality. It will not give electrical neutrality. So to maintain electrical neutrality, what we have to do? See here, I am writing. Let's observe here clearly. Now among these 99, now how many I am writing? 97 I am writing. 97 Fe plus 2. Already one Fe plus 2 is missed here. Now 97 written. 97 means how much it is? 194 positive charges are present now. But among these only 99, 97 I written now. So 2 Fe plus 2s are now converted to Fe plus 3. So how many irons are present? 97 plus 2, 99 only. One is missed there. It is missing from its original site. So now to maintain electrical neutrality, among 99, 2 more Fe plus 2s are converted to Fe plus 3. Now how many? 2 into 3, it becomes 6 positive charges. Total how many positive charges now? 200. 200 positive charges. If you are not understanding this, then just observe this. Again, you are not understanding means one more time you have to see the video. You can get clarity. Here 100 Fe plus 2, 100 O minus 2 in the beginning. So positive charges, negative charges are equal. So it maintains electrical neutrality and it is stable now. But whenever one Fe plus 2 is missing, then number of Fe plus 2 are 99. Number of oxygens are not changed here, remains as. Therefore 198 positive charges, 200 negative charges, which is not equal. So number of negative charges are more. Therefore it is not stable. But whenever it maintains electrical neutrality, then again it can get stability. So to get stability, here what I am doing for understanding, only I am giving this explanation for understanding purpose. From this 99, 2 iron plus 2 are equal to Fe plus 3. So that I written 2 Fe plus 3 and remaining 97 Fe plus 2. If you observe here, 97 into plus 2, 194 here. 2 into plus 3, 6. The total now it becomes 200. And oxygens remain same. How many? Each oxygen minus 2 and 100 oxygens are present. Therefore, 200 negative charges are present. 200 positive charges, 200 negative charges. But one iron is missed here. But charge is not eliminated here. Charge is same. Here in the beginning, how many charges are present? Negative and positive. At the end also, positive and negative charges becomes same. How it is happens means it is 2. See here, to maintain electrical neutrality, some of plus 2 ions are changed to plus 3. Lower valent metals are changed to higher valent metal to maintain electrical neutrality. This concept is very important. From this, every time I am observing one question. What is the fraction of Fe plus 2, Fe plus 3? Otherwise, nickel plus 2 or nickel plus 3. In particular compound. In particular compound, here I am taking one example. See, this question is important. Here I am writing question, I am giving solution. After that, similar questions you have to practice. Wait a minute. What is the fraction of Fe plus 2 and Fe plus 3 present in Fe 0.96 O? That is the question. 0.93 O also you can take. That is nickel. What is the fraction of nickel plus 2 and nickel plus 3 in nickel 0.94? Yes, sulfur charge is again like oxygen minus 2 only. Here we have to use oxidation number concept. In redox reactions first year, we have oxidation number topic now. That concept you have to apply here. See here, I am writing question. What is the fraction of Fe plus 2 and Fe plus 3 present in Fe 0.96 O. This is the compound given. That means instead of 1 Fe, because of this defect, now number of ions becomes 0.96 and oxygens remains as here 1 oxygen only. 1 oxygen only. Okay. For this, we have to use oxidation number concept. See here total 0.96 irons are present. Among these 0.96 irons, sum of irons are Fe plus 2. Sum of irons are Fe plus 3. For example, Fe plus 3 irons I am taking as X. If Fe plus 3 are equal to X, then how many Fe plus 2 are present? Number of Fe plus 2 means among 0.96, number of Fe plus 3 ions are X. Remaining are Fe plus 2. Remaining means out of 0.96, after removing this X, that is remaining means here 0.96 minus X. This is nothing but number of Fe plus 2 ions. Oxygen minus 2 ions as usual, there is no any change here. 1 oxygen minus. This is important. This you have to understand first. How many Fe plus 2 ions are present? Number of Fe plus 3 ions I am assuming as X. Fe plus 2 ions are 0.96 minus X. O minus 2 are 1. Okay, now this concept, sum of oxidation numbers of all the elements, otherwise all the atoms present in the compound is equal to 0 for neutral compound. See, this is neutral only. It maintains electrical neutrality just now given. So this is the compound which is in neutral state. So this is one of the rules in finding oxidation numbers. In redox reactions concept first year, just go through the rules. This is one of the rules. Sum of oxidation numbers of all the atoms present in the compounds is equal to 0 if it is neutral. Neutral compounds. This is for neutral compounds. For charged compounds, sum of oxidation numbers of all the atoms present in any polyatomic ion equal to its ionic charge. Equal to its ionic charge. Even though it is positive charge or ion negative charge, we have to equate it to that charge. Neutral species have 0 charge, so that we have to equate to 0. So how it is? See, simply I am giving this example. H2SO4 if you take. So this is neutral. We have to find sulfur oxidation number. Means how we can find? You know, each hydrogen plus 1. For 2 hydrogens it is plus 2. And we have to assume it as X minus. Each oxygen you know minus 2. 4 oxygens are there, so it is minus 8. So this is neutral, so that we have to equate is to 0. Similarly here also. See here plus 3. Plus 3, how many? X are there. Number of plus 3 answer X. See number of hydrogens are 2 no? 2 into plus 1 hydrogen 2. 1 sulfur, it have to assume as X, so that X only. But here 4 into minus 2 minus 8. Similarly here also, how many are there? X. So that plus 3 ions are X, so that 3X. Plus, how many plus 2 ions are there? Plus 2 ions are this many. So that plus 2 into 0.96 minus X. And how many negative ions are there? So plus here. Plus only 1. 1 into minus 2 equal to 0. Plus 3X plus 2 into 0.96 minus X plus, because sum of oxygen numbers, so that here also plus, but finally plus into minus it becomes minus only. So here again I am writing plus 3x plus 2 into 0.96, how much it is? 1.92 I think. 1.92 minus 2 into x, 2x minus into plus, it is minus 2 equal to 0. Then here minus 2x is there, here plus 3x, so it is x. X plus 1.92 equal to, whenever this minus 2 goes that side, becomes plus 2. Is 2. So x plus 1.92 equal to 2. Then x equal to how much? X equal to no 2 minus 1.92. Here now x equal to 0.08. 1.92. It is 0.08. Right. Then 0.08, this is x. X is nothing but Fe plus 3. But it is not fraction. It is not from the fraction. They are asking what is the fraction they are asking. Means fraction, whenever they are asking, we have to consider as 1, not 0.96. Here we got 0.08 from 0.96. If they ask what is the Fe plus 2 and Fe plus 3 present in Fe 0.96 if they ask this much, then this is the answer. But they are asking about what is the fraction among these. Fraction means this 0.96 is considered as 1. Percentage means that 0.96 is considered as 100. If they ask what is the percentage of Fe plus 2 and Fe plus 3, then that 0.96 equal to 100, then this much equal to how much it is. Like that you have to calculate. See here I am giving, this is x, that is nothing but Fe plus 3. So here this is not fraction, this is just Fe plus 3 in 0.96. Here fraction of Fe plus 3 I am calculating now. Fraction of Fe plus 3. But here 0.08 is nothing but Fe plus 3 quantity only, but present in 0.96, not in 1. So what I am doing, this 0.96 what they given the question is considered as 1, because fraction. If this percentage equal to 100, and how much you got x value plus 3 is now 0.08. 0.08 equal to how much? Otherwise, if it is 100, then we have to equate it into 100. Otherwise, after getting this fraction, if you multiply with 100, you can get percentage. Sometimes even though if they ask fraction, in the options they give percentages, then we can take 100. So 0.96 equal to 100, then 0.08 equal to how much? Just you have to do simply cross multiplication. So that Fe plus 3 fraction equal to 0.08 into 100 by 0.96. This is the Fe plus 3 quantity if we consider Fe as 1, not 0.96. If you consider Fe 0.96, this is only the answer fraction. If you consider it as 100, then you can get percentage. How much it is? 0.08 into 100 by 0.96, it is, you got 8.33. 8.33 percentage of Fe plus 3 ions are present in Fe 0.96 O. Then both they are asking, no, Fe plus 3 you got now. What is Fe plus 2? No, Fe plus 2 is nothing but remaining. Remaining from percent means 100 minus 8.33. 100 minus 8.33, it is 91.66. 91.66. Like this you have to do. After that, just to practice by taking other questions like Fe instead of 0.96, just to take 0.94 S. For sulfur also minus 2 charge. For one oxygen item minus 2 no. If you take sulfur, there also you can take S minus 2. Similar concept you have to apply. Redox reaction concept you have to apply. So like these questions I observed in previous examination papers. Please go through this. Okay, remaining concepts in next classes we'll discuss. Thank you.